Okay, good morning everybody. We are on to our last topic now, atomic physics. Yay. Let's turn to our textbook, page 244. So from the name of the topic, you know that we're going to be learning about atoms. Okay, the first part will be the atomic model. So now, a bit of history, okay, about the different models of atom. So right from the start, the Greek philosopher Democritus suggested that all matter was made out of tiny indivisible particles, and they call it atom, which means cannot be cut or divided. Then in 1803, somebody else proposed that actually atoms are tiny hard spheres. And so that's Thomas Dalton. And he also proposed that every element was made up of the same atom. So if it's a different element, it'll be made up of different atoms. Then in 1897, J.J. Thomson, now this discovery was important, he discovered the electron. He found that it was negatively charged and it was much smaller than the atom. So this discovery showed that atoms were not indivisible, they were made out of smaller subatomic particles. And based on his discovery, he suggested that atoms are made up of a ball of positively charged matter embedded with negatively charged electrons, a lot like plums in a pudding. For us, it would be like chocolate chips in a cookie, right? So this is known as the plum pudding model. Now in 1909, Hans Geiger and Ernest Marsden performed an experiment. What they did was they fired alpha particles. Alpha particles are positively charged particles, okay, onto a thin gold foil. And the results from the experiment showed that the plum pudding model was incorrect. So what did they observe? If they shot out alpha particles from the source through the gold foil, they noticed that almost all the particles went straight through the gold foil. There were some that got deflected by a small angle, and about 1 in 10,000 were deflected backwards. So how do we explain these results? Now the fact that there were deflections means that there is a force between the positively charged nucleus and the positively charged alpha particles. Okay. Second would be, most of the alpha particles do not go near enough to the nucleus to be deflected. And thirdly, the backward deflections occur when the alpha particles make a near head-on collision with the positively charged nucleus. So this, based on Geiger's and Marsden's experiment, Rutherford then suggested that atoms are not like the plum pudding model, but they're actually tiny positively charged nucleus that are surrounded by negatively charged electrons. And how Geiger and Marsden's results supported Rutherford's atomic model was that because of the relatively small number of deflections, it shows that actually most of the atom is empty space with a very small nucleus. The backward deflections can only occur if the nucleus is positively charged and it contains most of the atom's mass, and the plum pudding would not produce backward deflections. It would produce deflections but not backwards, because the masses were all spread out. Okay, so those were the different models of atom, and we finally, right now we are following Rutherford's atomic model. Okay, let's move on to the nucleus. Those of you who are taking chemistry, you can fast forward this part. Those of you who don't take chemistry, you need to listen to this. Okay, so we have the atom is made of 3 subatomic particles: protons, neutrons, electrons. Now please take note that these 3 particles are called subatomic particles. Alright. Now 4 new terms that you need to know: the atomic number, the proton number, the mass number, and the nucleon number. Now the atomic number means that this is the number that tell you what atom it is. And what is the number that tell you what atom this is based on the number of protons. Every individual element will have a fixed number of protons. No 2 elements will have the same number of protons. So the number of protons determine what kind of element it is. Okay, so therefore the atomic number can also be called the proton number. Now the mass number. The mass number tells us the number of protons and neutrons. Why is that so? Why don't we include electrons in the mass number? Because, the atom is made of protons, electrons, and neutrons, right? Why do we only consider the protons and the neutrons? Why don't we consider the electrons? Well, basically because protons and neutrons have got about the same relative mass. They've got about the same mass. But electrons are about 2,000 times lighter than protons and neutrons, which means that when you add the mass of the electrons in, the value is so small that it's insignificant to its mass. Therefore, we do not consider the mass of the electron. So the mass number tells us the number of protons and neutrons because these two are the heavier particles or subatomic particles. And the other name for mass number is called the nucleon number. Why nucleon number? Because the nucleons would mean protons and neutrons. Okay. So copy this down into your notes. Please take note of the symbols for each of these subatomic particles. You need to know where they are found in, their relative masses, and their relative charges. So protons, P, so it's positive. Neutrons, neutral, so no charge. Then you know electrons are negative. Okay, nuclear notation. These are the two ways we will, when you do your questions, you notice that the questions can either give it to you in carbon 14, or they will show this to you. So you need to understand what these two represent. Now when they tell you carbon 14, obviously the first name tells you the name of the element, carbon. What does 14 mean? 14 tells you the mass number. Okay, so it will be number of protons plus neutrons. Now if they give it to you in symbol form, so they write down capital C. Capital C is a symbol for carbon. So this one requires a periodic table, which the chemistry students will know. But if you don't take chemistry, don't worry, you don't have to memorize any of these. Usually the name of the element and the symbol will be given to you in the question. So all you have to know is to know how to interpret the values that accompanies the symbol. So there'll be two numbers, one number on top, one number at the bottom. The number at the top tells you the mass number, which tells you the number of protons and neutrons. The number at the bottom tells you the atomic number, which would be the number of protons. So when you're given this symbol here, basically you can find out the number of neutrons. How do I find the number of neutrons? I take the mass number minus the atomic number. So based on the symbol, it gives us 3 pieces of information. Now we move on to isotopes. Turn to page 245 of your textbook. The second line at the top, you will see that isotopes have the same atomic number but different mass numbers. Now how is that the same as what I've written here? Isotopes are atoms of the same element with the same number of protons but different number of neutrons. Now, first thing you need to know is that isotopes are the same element. How do I know they're the same element? Because they're the same number of protons. Remember just now I told you that number of protons determine what kind of element it is? So if you look at the diagram above, the example of hydrogen, we have 3 isotopes for hydrogen. Hydrogen 1, hydrogen 2, hydrogen 3. And some isotopes have got different names. So in this case here, hydrogen 1 is called hydrogen, hydrogen 2 is called deuterium, and hydrogen 3 is called tritium. Okay, so you notice that they have the same number of protons. 1 proton, 1 proton, 1 proton. Therefore, they are all hydrogen. But they have different number of neutrons. So hydrogen 1 has got no neutrons. Hydrogen 2 has got 1 neutron. Hydrogen 3 has got 2 neutrons. So they have different number of neutrons. Now if you look at your textbook, it says that they have the same atomic number. What is the atomic number? Atomic number is the number of protons, right? So that's the same atomic number. Then they said it has different mass number. Different mass number. Now remember, what is mass number made up of? It's made up of protons plus neutrons. But if number of protons are the same and number of neutrons are different, therefore the mass number should be different. So basically these are 2 different definitions, but they mean the same thing. Okay? Now can you try this out first? Pause here and try it out. So did you get this? So the first thing you need to know is that when you want to write it down in terms of its, when you want to notate this isotope, you need to be able to know what's the mass number. So mass number would be proton plus neutron, the number of protons plus number of neutrons. So you got to do that first. Then the number at the bottom here, remember, it tells you the number of protons. Over here, number on top tells you number of protons plus neutrons. Okay, again, pause here and try example 2. So they ask us for the number of protons and neutrons. Now remember the number at the bottom tells us the number of protons. So number of protons would be 7. Then how do I find the number of neutrons? Number of neutrons would be the top number minus the bottom number. So check this out. Did you get this? Should be easy, right? So basically this number would be top number, which is your mass number, minus bottom number, which is your proton number. Okay. Now something for you to take note of is that apart from the smallest atom, so like hydrogen, most nuclei have got more neutrons than protons. Okay, let's move on to nuclear fission. Now we briefly talked about this last year under the topic of energy. We spoke about nuclear fusion and nuclear fission. Now what is nuclear fission? Nuclear fission is a splitting of a nucleus. Now how do you remember that? Remember I told you that fusion comes from the word fuse. Fuse means to join together, right? So fission is just the opposite, means to split apart. Now, what are fissile materials? These are materials that easily undergo fission, and the most commonly used fissile material is uranium-235. Now, when uranium-235 undergoes fission, it produces two daughter nuclei called fission fragments. Now, of course, this process also produces a lot of neutrons, gamma radiation, and kinetic energy. Basically, it means a lot of energy, okay? A lot of heat. So let's talk about the fission of uranium-235, because this is what we normally use in our nuclear reactors. So how do I get a fission? How do I get my uranium-235 to undergo nuclear fission? It is not something that it cannot just get split apart like that. You need to have something to initiate it. So it needs to absorb a slow-moving neutron. So I have uranium-235. When it absorbs a slow-moving neutron, means it takes it in, right? What will be produced? You get uranium-236. How do I get uranium-236? I add the top numbers together, add the bottom numbers together. Since the bottom number still remains as 92, which means that it is the same element, right? So it's still uranium. So this is an isotope. Now uranium-236 is very unstable, so it splits apart. And it gives us two different fissile fragments. So once again, take the top numbers, add them together. Take the bottom numbers, add them together. Do you get what is given on the left-hand side? So if you take 144 plus 89, you notice that you get 233. But on the left-hand side is 236, which means that at the top here, I should still have three particles. Now, take the bottom numbers on the right-hand side. 56 plus 36. You get 92. Does it match? It matches, which means that basically I have no more protons, but 3 neutrons, right? Because the bottom number tells you the number of protons. So you know that, so what you know is that there are going to be some neutrons that will be produced. Okay, and how many neutrons will be produced? 3 of them. Because each neutron has got only one the mass number will be 1 and the proton number is 0. Okay, and then lots of and then some gamma radiation.